In this video, I'm going to draw several Lewis structures and name the molecules, starting with O2. The name for O2 is simply oxygen. It is sometimes known as molecular oxygen or oxygen gas. This particular element exists as two atoms bonded together. We call that a diatomic molecule. And there are 7 elements that exist this way: hydrogen, nitrogen, fluorine, chlorine, bromine, iodine, and oxygen all exist this way. Oxygen is in group 6A. That is the 16th column on the periodic table, but it has been simplified to simply 6A. That tells me that it has 6 valence electrons. All of the elements in group 6A have 6 valence electrons. Valence electrons are the electrons used for bonding. Oxygen is one of the elements that wants 8 valence electrons to be like its nearest noble gas. That means that oxygen wants 2 more electrons. If oxygen is with a metal, then it can take 2 electrons away from one or more metal atoms. If, as in this case, the oxygen atom is bonding to another nonmetal or metalloid atom, it needs to share those electrons and then make 2 bonds. To start my Lewis structure, I will simply draw a single bond between the 2 oxygen atoms. At this point, I ask myself, are these oxygen atoms happy? No, they want 2 bonds. If you have two atoms next to each other that each want another bond, you go ahead and give it to them. Now, at this point, they're happy in terms of bonds, but they've only used 2 of their valence electrons each. That means they still have 4 valence electrons left over. I will draw those 4 valence electrons in pairs, giving each of them 2 sets of lone pairs. 2 bonds and 2 lone pairs. Lone pairs, that's the term we use for the pairs of electrons that are not forming bonds. The valence electrons that are still there that are not forming bonds. Call them non-bonding valence electrons. Sulfur is going to want to do the same thing to form 2 bonds and have 2 lone pairs left over. This is the final Lewis structure for oxygen. Carbon dioxide is next. When you are naming covalent molecules, especially simple ones like this, then except for oxygen, we just call the element by its name, carbon. If it has more than one atom in the molecular formula, then we use prefixes, and those include things like di, tri, tetra is for 4. In this case, we will simply name the carbon as carbon, and then space, and then dioxide. Because there are 2 oxygens, the second element's name will end with IDE. I will start with carbon in the center. Carbon is in group 4A, which is the 14th column on the periodic table, but it's simplified to 4A. That means that carbon has 4 valence electrons. The element silicon is under carbon. It also has 4 valence electrons. Carbon, like the other nonmetals, want to have the same number of valence electrons as their nearest noble gas. That's going to be 8 for carbon. Well, technically neon. That means that carbon needs 4 more valence electrons for a total of 8. If carbon is with metal atoms, then it will take those 4 electrons. But if it is with other nonmetals, which oxygen is, or metalloids, then the carbon simply wants 4 bonds. We've already talked about oxygen. Oxygen wants 2 bonds and 2 lone pairs of electrons. It's extremely rare for carbon to have any valence electrons left over because carbon gets 4 bonds and it will use the 4 valence electrons it has to make those 4 bonds. I'm going to put carbon in the center and I'll put an oxygen on each side. The oxygens want 2 bonds. They're next to someone who wants more bonds, so I will give them that extra bond. On this side as well, oxygen wants another bond. Carbon also wants another bond, so I give it to them. Then the carbon has used all 4 of his valence electrons. He's done. There's no extra non-bonding electrons. The oxygens, however, have only used 2 of their 6 valence electrons, so I will draw in the other 4. There they are again with 2 bonds and 2 lone pairs, and carbon is extremely happy with his 4 bonds and no lone pairs. The next molecule is CCl4. We have 2 non-metal elements bonding, so I know it's going to form covalent bonds. With that in mind, I will name the carbon just by his name because there's only one of him. The chlorines have 4. The prefix for 4 is tetra. I know that's an unusual prefix, but there you have it. And the name for chlorine is going to change to chloride, ending with IDE. We already know carbon is in group 4A. Chlorine is in group 7A. This is the 17th column on the periodic table, but it's been simplified to simply say 7A. That means that chlorine has 7 valence electrons. He's only 1 electron away from being like his nearest noble gas. That means that he just wants 1 bond. If he was with a metal, he would take an electron away to get the extra. But he's not. He's with a nonmetal or metalloid, so he just gets to have 1 bond. That means that some of the time he'll get to have an extra electron and be completely satisfied. As usual, we're going to put the carbon in the center, and I will put a single bond to each of the 4 chlorine atoms. At this point, I will ask myself, is everybody happy with that 1 bond? And carbon with his 4 bonds? Yes, they are. So in terms of bonding, I am now done. The carbon has once again used all 4 of his valence electrons and is fat and sassy, just sitting there. No extra non-bonding valence electrons to draw in. But the chlorine atoms, they started with 7. They've used only 1 to form that bond. That means that each of these chlorine atoms has an additional 6 valence electrons. Note where I'm drawing them. I do not draw the 2 electrons on this side. That side's already full with the 2 electrons in the bond. I draw the other 6 electrons like a picture frame around the atoms. And we go zooming around, filling in all those valence electrons. And now our carbon tetrachloride is complete. The elements in group 7A will have 1 bond and 3 lone pairs of valence electrons that are not involved in bonding. So again, we have oxygen, group 6A, will have 2 bonds and 2 lone pairs. Carbon in group 4A, 4 bonds, no lone pairs. Silicon will be the same way. Chlorine, bromine, iodine, fluorine, they're all in group 7A. All of them will form 1 bond and 3 lone pairs of electrons. The next molecule is C2Br4. Bromine is in group 7A. So he's just like chlorine, 7 valence electrons, and will form 1 bond and 3 lone pairs. The tricky part on this one was the carbon. Still going to want 4 bonds, but with the 2 carbons there, they go in the center. And we're going to be fair. We're going to put those 4 bromines around those 2 carbon atoms, giving them each 2. We share electrons and we share those atoms that they have bonded on them. Let's check and see if everybody's happy with their bonds. The bromines are. They form the 1 bond, which gives them the 1 extra valence electron they need to be like their nearest noble gas. But carbon's not happy, and we don't want to make carbon unhappy. I see 2 carbon atoms, 1, 2, 3 bonds on them. I always look up, down, and all around to count the number of bonds. There's only 3 on that one. There's only 3 on that one. They each want 4, so I give them the extra bond. Everyone is now happy with their bonds. The bromine atoms came to the party with 7 valence electrons. They've only used 1 in the bond with carbon. That means that just like chlorine, fluorine, and iodine, they will be drawn with 6 additional valence electrons around them. 3 lone pairs of electrons. And again, notice that those electrons are going like a picture frame around it, and they are not on the side where the bond is to carbon. The next molecule I'm going to draw is BF3. The name for the element that's symbolized with the letter B is boron. F is for fluorine. There are 3 of them. The prefix in a covalent molecule like this one is going to be tri. Tri means 3, and the name for fluorine changes to fluoride. The second element's name ends with IDE. I know that boron is a metalloid and fluorine is a nonmetal. When they combined, just like 2 nonmetals, they form covalent bonds. So this is a covalent molecule. The boron is in group 3A. This is the 13th column in the periodic table, but it gets simplified to 3A. That means that he has 3 valence electrons. Boron is an exception to the rule. At this level of understanding, boron will never have a total of 8 valence electrons. Boron does not lose electrons like aluminum does beneath him because boron is not a metal. Therefore, the best boron can do is form 3 bonds. He'll also have no lone pairs of electrons remaining. He'll use his 3 valence electrons to form 3 bonds, and then that's the best he can do at this level. The fluorine is in group 7A. So just like the other 2 that we've done so far, chlorine and bromine, he will have 1 bond and 6 lone pairs. Sorry, 3 lone pairs, a total of 6 electrons left over. I will put boron in the center. He wants more bonds, so he goes in the center. I'll draw those fluorine atoms in. I'll check and see if everybody's happy with their bonds. Boron has the 3 bonds that he is able to make. Each fluorine atom has the 1 bond that they want. Boron has no lone pairs left over, no extra electrons that aren't involved in bonding, but fluorine has 6. So we will fill those in, and we are now done with this structure. The next molecule that I'm going to help you with is CH4. Instead of calling this carbon tetrahydride, instead it has a name that we give for organic molecules. The name for this compound is methane. Methane is a covalent molecule because carbon and hydrogen are both nonmetals. Carbon is in group 4A, which means that carbon will have 4 bonds and no lone pairs. Hydrogen has only 1 electron. That's it. Not in terms of valence electrons, he just has 1 electron. Now, it is considered a valence electron involved with bonding. Hydrogen can only make ever 1 bond. It's going to be 1 bond and no lone pairs. Carbon wants the most bonds. I'll put him in the center. I'll put those hydrogen atoms around the outside. Carbon has used all 4 of his valence electrons. There are no extra electrons remaining. The hydrogen atoms have used their 1 electron that they possess, and there are no electrons left. Therefore, this molecule's Lewis structure is complete. The next molecule is sulfur, S, and 2 bromines. The name for S is sulfur. And we've seen that the name for bromine is, Br is bromine. There are 2 of them. This is a covalent molecule because sulfur and bromine are both nonmetals. I will therefore use the prefix that means 2, di. I will change bromine's name to be bromide. Sulfur is like oxygen. Sulfur is in group 6A. That means that he wants 2 more electrons to be like the elements that are in group 8A. He wants 2 more electrons, so he's going to form 2 bonds. Bromine will have 1 bond and 3 lone pairs. Sulfur once more, so I'm going to put the sulfur in the center. I will put the bromine atoms around him, and I will check to see if everybody's happy with their bonds. Sulfur wants 2 bonds, he has the 2 bonds. Bromine atoms want 1 bond, they have their 1 bond. Everybody's happy with their bonds. Now I just fill in the extra electrons. I've already said that the bromine atoms will have 3 lone pairs. I'll draw those in like a picture frame around the symbols for those elements. The sulfur atoms, they want 2 more. They had 6 valence electrons to start with. So just like oxygen, they want 2 bonds and 2 lone pairs. The 2 bonds account for 2 electrons, and now I fill in electrons 3, 4, 5, and 6. This Lewis structure is now complete. The next molecule I'm going to do is PF3. The name for P is phosphorus. There's only 1, so I'll just write phosphorus. And he shops at Toys R Us, so I need to correct the spelling. Phosphor, Toys R Us. There we go. And there are 3 fluorine atoms. The prefix for 3 is tri, just like triangle or tricycle or tripod. Trifluoride. Fluorine has the flu, so that's why I do FLU, and then I finish spelling it oride. Phosphorus. Phosphorus is in group 5A. It's the 15th column, but we simplify it to 5A. That means that phosphorus has 5 valence electrons. He wants 3 more. If phosphorus is with metal atoms, it will take 3 electrons, but fluorine is another nonmetal, just like fluorine. Fluorine is a nonmetal, just like phosphorus. Therefore, they will share electrons. And that means that phosphorus wants 3 bonds. The fluorine atom, as we saw before, fluorine will have 1 bond and 3 lone pairs. Phosphorus wants more bonds. I'll put him in the center. I'll start with a single bond to each of the fluorine atoms. Now I'll ask myself, are they happy with their bonds? Well, phosphorus needed 3 more electrons. He wanted 3 bonds. He has 3 bonds. The fluorine atoms start with 7 valence electrons. That means they just need 1 bond. And boom, they each have it. They're happy with their bonds. I'll now fill in the extra valence electrons. The fluorine atoms, they've used 1 of their 7 original valence electrons to form the bonds with phosphorus. That means they still have 6 remaining valence electrons that need to be drawn in. The phosphorus atoms are in group 5A. They have 5 valence electrons. So far, this guy's only shared 3. That means numbers 4 and 5 need to be drawn in as 1 lone pair. So phosphorus, like nitrogen, who's above him on the periodic table, is going to form 3 bonds and 1 lone pair. The next molecule I'm going to draw a Lewis structure for is HCN. This has a few names depending on whether it's in water or not. We're going to name this compound much as we would an ionic compound. We have the hydrogen, and then the group C and N. We learned from the ionic compounds that this is a polyatomic ion. His name is cyanide. So even though we're bonding with a nonmetal hydrogen, the name for this compound is going to be hydrogen cyanide. In water, some cyanide ion will form. And then the hydrogen will also form an ion too. But just a little bit. When they stay together as a covalent molecule, they will be covalently bonded together. Hydrogen, he gets 1 bond only and no lone pairs. Carbon only gets 4 bonds, no lone pairs. Nitrogen. Nitrogen is in group 5A, just like phosphorus. That means he starts with 5 valence electrons. He wants 3 more. We're adding up to 8. If nitrogen is with metals, then he will gain 3 electrons. But he's going to be bonded to carbon, who is another nonmetal. Therefore, he wants 3 bonds. He'll be able to share 3 electrons with carbon. 3 bonds. There we go. I'm going to put carbon in the center because he wants 4 bonds. And this formula has given me a clue. I'll put a hydrogen with a single bond there, and I'll put a nitrogen with a single bond on this side. Let's see if everybody's happy with their bonds. Hydrogen is. He's got his 1 bond. Carbon is not. He only has 2 and wants 4. Nitrogen. Nitrogen has 1 bond currently, but he wants a total of 3 bonds. Let's do this. Let's give it to them. Nitrogen now has 2. Carbon now has 3. Nitrogen now has 3. Carbon now has 1, 2, 3, 4 bonds. Carbon's happy. Nitrogen's happy. This is known as a triple bond. Carbon and nitrogen are famous for doing this. Either to themselves or to each other. Nitrogen, 5 valence electrons, we've only drawn 3. That means I'm going to draw an additional 2 electrons on the nitrogen to account for all 5 of his valence electrons. Carbon won't have any. He already used his 4 valence electrons to make the bond. Hydrogen again, he came with 1 electron. He shared his 1 electron. No extra unpaired electrons. This is the final Lewis structure for hydrogen cyanide. The next structure is CH3Cl. Carbon, 4 bonds, no lone pairs. Hydrogen, 1 bond, and no lone pairs. Chlorine is in group 7A. I don't think we've done him yet. Group 7A. That means he has 7 valence electrons. He wants 1 more. He's bonded to a nonmetal atom, to carbon. Therefore, he's going to make 1 bond. If chlorine is with metals, then he will take that extra electron, but he's not. He's with carbon. Carbon wants 4 bonds. He goes in the center. We'll put, it doesn't matter where you draw the hydrogens and chlorine atoms. I'll put the hydrogens off to the top, left, and bottom, and I'll put the chlorine atom here on the right-hand side. The hydrogen atoms are happy with their 1 bond. The carbon is happy with his 4 bonds. The chlorine is happy with his 1 bond. Yay! Hydrogen atoms have no extra valence electrons to draw on them. Carbon has used all 4 of his, so there's no lone pairs to draw on him. Chlorine has used only 1 of his valence electrons to form this bond, which means he still has a total of 6 valence electrons to draw in. They come as 3 lone pairs, so chlorine will have 1 bond and 3 lone pairs of electrons. That's the final structure for this compound, which is known as methyl chloride or chloromethane. This is something, see, we've seen that methane before when we have 1 carbon and hydrogens around him. Now we have a chlorine replacing the hydrogen, so the name becomes chloromethane, or methyl for the CH3 portion, and then chloride for the second nonmetal's name. We have one structure left. We have C2H2Cl2, and I gave the note that we're going to put one hydrogen and one chlorine on each of those atoms of carbon. Carbon, hydrogen, and chlorine, I've already put all the notes there. So I'm going to put the two carbons in the center, single bonded to each other. I'll give each carbon one hydrogen, and I'll give each carbon one chlorine. I'm doing this because that's what we were told in the instructions to do. I could have put two hydrogens on one carbon and two chlorines on the other. I needed the instructions to tell me what to do. And in fact, the name that I gave you also tells you how to put them. I said 1, 2. That tells me that carbon number 1 and carbon number 2 will each have a chlorine. I use the prefix di because there's two chlorine atoms, dichloro. And this connection between the carbon and the extra bond they're about to make gives us the name ethylene. 1,2-dichloroethylene, and that 1, 2 is important so that I know one chlorine goes on each carbon atom, carbon number 1 and carbon number 2. We've said that the hydrogens want one bond, they each have it. The carbons want 4 bonds. Uh-oh. If I look up, down, and all around, those chlorines only have 3 bonds. 2 atoms next to each other that each want one more bond. I'll give it to them. Now the carbon atoms are happy with their 4 bonds. The chlorine wants only 1 bond. He has his 1 bond. Everybody's happy with their bonds. I now have no lone pairs on carbon. That's perfect. No lone pairs on hydrogen. That's perfect. Chlorine wants 3 lone pairs, so I'm going to give it to each of these chlorine atoms. 3 lone pairs, or a total of 6 non-bonding valence electrons. This is the final structure for 1,2-dichloroethylene. And we're done. Give me a moment as I pause the recording, and I hope this was helpful for you.